Welcome to this explainer. Today, we're taking a massive leap. We're moving from that theoretical paper computer we built back in Unit 3 right into the actual commercially built reality of the 8085 microprocessor covered in Unit 4. So if you've been wondering what those abstract registers and buses actually look like when they're etched into a real piece of silicon, well, you're in exactly the right place. We're going to bridge that gap between concept and concrete hardware. Here's our roadmap for today's explainer. First, theory meets reality. Then, inside the 8085 architecture. Third, pin configuration. Fourth, the programmer's view. Fifth, instructions and data. And finally, write, assemble, execute. Let's get into it.
Section 1. Theory meets reality.
Now, the 8085 might sound intimidating, but I promise you it's not some scary, entirely new concept. It's literally just a concrete, physical manifestation of the exact same fetch, decode, execute skeleton that you already mastered in Unit 3. Think about it. The accumulator, the program counter, the instruction register, they're all still right here. The only real difference? Our conceptual paper computer now has a legitimate part number and physical electrical boundaries.
And you can see this seamlessly reflected right here in the syllabus. Notice how we shift directly from Unit 3's Basic Computer Organization and Design straight into Unit 4's Introduction to 8085 Assembly Language Programming. It's one continuous narrative, really. The concepts of timing, control, and instruction cycles you just wrapped your head around, those are the exact operational rules that the 8085 abides by.
Moving right along, Section 2. Inside the 8085 architecture.
So, at a macro level, the internal block diagram of the 8085 is an absolute masterclass in organization. It features all those familiar components you'd expect. You've got your arithmetic logic unit, the ALU, paired directly with the accumulator to handle the math. But here's a fun addition. We introduce a flag register to essentially keep score of our math results. We've also got 6 general-purpose registers, B, C, D, E, H, and L, which can cleverly team up and act in pairs. Throw in the stack pointer and program counter to track our position, an instruction register and decoder to read what's coming next, and a timing and control unit to sequence that classic fetch, decode, execute rhythm. All of this is tied beautifully together by internal data and register buses.
All right, Section 3, pin configuration.
So, the key takeaway here is that the 8085 layout, which usually comes in a dual inline package, has exactly 40 pins. Now, confidently speaking, please do not feel like you need to memorize every single one of these 40 pins right now. We're just taking a high-level conceptual pass to understand how they all function together.
What's really fascinating here is how we can group these 40 pins by their neighborhoods or their specific jobs. For instance, we have pins entirely dedicated to the address bus, passing 16-bit locations over to memory. Then we have a super clever multiplexed address and data bus that actually shares pins just to save space. We've got control and status signals like read, write, and address latch enable, managing all the traffic. Throw in your power and clock signals, 5 dedicated interrupt pins, including the non-maskable trap, and some serial I/O pins, and boom, you have the complete picture. By focusing on the shape of the system rather than the micro details, the whole chip makes a lot more sense, right?
Which brings us to Section 4, the programmer's view.
When you sit down to actually write code for the 8085, you aren't interacting with every single wire inside of it. That would be overwhelming. Instead, we define what's called the programming model to filter out all that noise. This is strictly the subset of tools the programmer actually has control over, purposefully ignoring the deep internal wiring, like the instruction decoder or those internal data buses. As a programmer, your sandbox is limited exclusively to these specific items. First up, you have the accumulator, which is for your primary operations. Then you've got those 6 general-purpose registers, but keep in mind, you'll very often use them as 16-bit pairs, BC, DE, and HL. You also have the 5 flag register keeping score, letting you know if a result is 0, negative, or if it caused a carry. And finally, you have the stack pointer for managing subroutine memory and, of course, the program counter, tracking your exact instruction position. This specific list right here, that's your entire tool belt.
Next up, Section 5, instructions and data formats.
The 8085 has roughly 74 primary instructions, but again, don't worry, they do not need to be memorized yet. Just recognize that they fall really neatly into these 5 families. You have data transfer for moving things around, like MOV or MVI. You've got arithmetic for math, like ADD or sub, logical for bitwise operations, like ANA or XRA, branching to jump around your code, like JMP or call, and finally, machine control to do things like halt.
Categorizing them like this makes the entire language incredibly approachable.
Now this visually breaks down how instructions actually exist in memory. Some commands are super simple and only take 1 byte, just the opcode itself, but others need data or addresses, which expands them into 2 or 3 byte instructions. The program counter really does all the heavy lifting here. It smoothly auto-increments to fetch sequential bytes. So it might fetch the opcode on step 1, the lower order byte of an address on step 2, and then the higher order byte on step 3.
Finally, Section 6, Write, Assemble, Execute.
This smooth end-to-end workflow is exactly why we even learn assembly in the first place. You start by writing human-readable mnemonics. Then, you look up the opcodes to hand-assemble it into hexadecimal machine code. From there, you load that hex into a specific starting address in memory. And finally, you let the 8085 execute it while you trace exactly what happens in the registers step by step.
Let's actually grasp the flow of a simple program using this addition example. First, we move immediate, the hex value 32, into the accumulator. Next, we move immediate 45 into register B. Then we add B to the accumulator, which gives us 77 hex. After that, we use store accumulator direct to push that 77 into memory location 2050. And finally, we halt. It's elegant, it's sequential, and honestly, it sets us up perfectly for analyzing much more complex addressing modes later on.
So, to wrap this up, the 8085 is really just Unit 3's computer made real. In our upcoming deep dive explainer, we're going to hand-assemble real code step by step. We'll trace exactly how those 5 flags react to our math, and we'll even use the decimal adjust accumulator, or DAA instruction, to loop right back to Unit 1's binary-coded decimal addition rules. Reviewing this high-level architecture today gives you the absolute perfect foundation. So, the only question left is, are you ready to jump in and command the silicon?